Well, good evening, ladies and gentlemen. It's not a best position to be a last presenter, but because everyone is waiting for the finishing. But anyway, yeah, well, well, obviously we heard a lot today about the simulation and modeling. We heard about the digital twins, all these aspects of digital shadow, the data science, which comes towards us in physics and engineering. And this is one of the application of data science. I'm coming from a background of numerical simulation, so I'm a computational mechanics man. But we do a lot of this data science techniques these days for real-time modeling to really incorporate ourselves into this digital twin aspects. So yeah, so what I'm going to talk about is, well, I'm going to talk, but I introduce LKR, where I'm working as part of the ASEAN Institute of Technology. Then I talk about a little bit about the material processes quickly, and then start talking about this reduce and real-time models, which are the data science models for the material processes. And then I show you two use cases, two case studies, real-world case studies on the material processes, and also the future developments. So LKR, yeah, we are a sort of a organization. LKR comes from a sort of a light metal competence center. So this in German. So we are sort of dealing with the processes of the light metals. We are a sort of a small, but we are 100% part of a ASEAN Institute of Technology. Now, obviously, on material processes, we do a lot of material processes. You might be familiar with the manufacturing processes, casting, extrusions. These days, additive manufacturing, printing, 3D printing, which is one of the new aspects of the manufacturing, which obviously brings a lot of type of opportunities with the future type of a remote manufacturing, all this digital manufacturing, every aspects are sort of coming together with this additive and printing manufacturing aspect. So, um, hello, next one. Yeah, okay. So for these processes, obviously, as I said, there are normal, what we do in normal conditions is you have a process experimentally. We do some numerical simulation using a finite element, CFDs. And now we obviously to get into this digital shadow and controlling and twinning aspects, we try to generate some data to really go and generate the uh, data models for these processes. They are really, really fast compared to what we do on the simulation aspects. Uh, so if you look at these processes, you see the videos. The top one is this 3D printing or additive manufacturing, and you see the obviously the numerical simulation of it. This is not a normal simulation because the domain is increasing or expanding in time. So this is not a fixed domain simulation. This is a dynamic generation model or finite. This is a special type of simulations. Again, on casting, that's the same things. This is uh, type of a time expanding time domain. And on the obviously on the right hand side, far right, you see this macrostructure developments module, which works within these simulations, and that's called the multi-scaling simulation. And then bottom, obviously, is the extrusion process. So on a reduced model for this, well, obviously, when you look at these simulations, this is they sometimes takes hours to really get any response and results for us. So they obviously cannot be used on real-time controlling or real-time digital twins, active digital twins. They are really, really time-consuming and they take a lot of computational efforts. So we sort of turn to data models. We have obviously different type of model building technologies from eigen-based builders, from kriging, symbolic regression. The people who are sort of familiar with the reduced models, they know there are obviously different data techniques which you can build your model based on the existing database. And there are different ways of doing this. Depends on what sort of data you have and what sort of application, real world application you have on your hand. So what happens is obviously the framework. When you design the framework, you have a type of a process which you want to generate a digital shadow of it. You want to control, active control, real-time controlling. And obviously, based on that, you have some offline databases based on your experiments, based on your numerical simulation, verified numerical simulation, and you have some live data coming from your sensors. And that's the feedback, live data you get. Then, based on that, you can build this real-time modeler, controller, and validation type of framework. So the technique essentially works like this. You choose your, obviously, data science technique or the model builder techniques. You have to have a data, and for that data, you need to generate some scenarios. So let's say if I have a process to run, I have different parameters, temperature parameters, speed parameters, material parameters. So I need to really have some data already in the database based on different variation of these parameters. And this is called the snapshot matrix. So you have some snapshot matrix, you run some simulations offline and get these results out into some databases. And then out of that database, you start making that real-time modeling and real-time models. Then you have to validate your model. You need to get the confidence that your real-time model, which works in fraction of a second compared to hours of numerical simulation, that needs to really give you some confidence, 99% confidence on the accuracy and reliability. So that's how the system essentially put together. So, and also it's for processes and sub-processes. If you are familiar with material processes, you know that we have a process and sub-processes like cooling. Normally you have a cooling or heating during the processes. You have solidifications. It means that the melt becomes a solid. That's the process state of material would change during the process. So it's not just for the processes you try to generate these real-time models. It's a sub-processes included into this processes, which needs to be we need to really make a fast model out of them. So for now, I sort of wanted to give you some sort of a real life case studies where we tested this reduce and real-time models. First one is for the 3D printing, for the additive manufacturing. If you can, I mean, obviously we have some experiments already. These experiments we measuring during the experiments some temperatures, some aspects, some parameters would be measured. These measurements would be used to really validate and calibrate our numerical simulations. Those validated simulations would really then run for the different combination of the parameters you see on the snapshot matrix or a scenario matrix here. So these things are run with this finite element, but finite element is initially validated using the experimental data. Then obviously you have the database. We used here a commercial software. This is a reduced model builder called Lunar. That's got different type of technique for the reduced model building. This is, you can essentially use it for the solver and interpolator. Now, what we've done here is we run some finite element analysis. We generated the builder. Then we run another set of finite element analysis. We call it DOE, design of experiments. So the builder, the model, the real-time model, it didn't know about the new cases. And then we compared the finite element results with this new finite element results with the models and real-time model. And that's the results you see almost fitting on top of each other. And you see the normalized errors on the right-hand side. The running time for the, let's say, finite element on the, let's say, on this additive manufacturing, something is around something 2,900 seconds, about 45 minutes, while on the MOR or a real-time model, it takes around zero 0.7 seconds to generate the similar transient results. So that's how fast these models are working in reality compared to the finite element. Sorry. Then the things you've seen before, there was temperature. This is one is the stresses, so it's not just the temperature. Different aspects of the process can be sort of modeled with these real-time models in a very, very fast way. On the extrusion, we done another case study. Again, similar. We done some experiments with some measuring things. Then we run some finite element of these experiments, calibrated our finite element, validated, and then generating this snapshot matrix with a different variation of the parameters. Run the base. The B here means the base scenarios. Means that these scenarios is used for to build the reduced model. The V is the validation. So this is a DOEs. The reduced model didn't know about the this extra simulations. Then we run this, and for the temperature, you see the temperature of the material particle as it goes through the end of a billet, through the tool and outside the billet. So the extrusion essentially works the billet pushed through the tool, and you get the final profile on the other side. So you're tracing the material temperature all across from the end of a billet to the profile, final profile, and the results of the DOEs and the reduced models, real-time models, and the finite element is almost matching. Again, you see the normalized errors on the right-hand side. So these reduced real-time models works accurate, works very, very fast if you have the right data on the database. And it's really, really revolutionizing the material processes now. We can put these real-time models incorporated into the digital shadow or digital twin, and you have a control. As soon as you have a real-time control of the process, you can control the process real-time without. So these very, very fast models are really beneficial. What we are trying to do as a future work is, obviously, we are working on the casting. So we're generating these reduced models for the casting, which is a difficult one because the casting is a little bit more difficult process. And then integrating these reduced models into digital twinning, as they are really in a digitalization era. This is really, really a fast models which we can implement into the digital twin. And obviously, there's a bit of a work which is not presented here, which with the machine learning, we really train the data as we get it as well, and as this reduced models generating the data, we would train it as well using the machine learning. This is called the hybrid reduced order models, which probably would be presented on the different presentations. Okay, so thank you very much. Sorry for the.
Thank you also for your patience to stay all day long up to the end. We need to